Okay, so the next thing I'm going to be talking about is the importance of forward momentum when shooting. So we're going to do a little practice problem. If Sidney Crosby was skating at 5 meters per second, then the puck on his stick would be traveling the same velocity. And then we're going to just suppose that Crosby launched the puck with 10 newtons of force. We're just going to assume that's what he's doing. That's how much our force he's exerting on the puck, and then we can determine from that the puck's acceleration toward the net, which would be 87 meters per second. The puck's final velocity would be 14 meters per second, and the work done by the stick is 1 joule, and then the power generated from this whole shot is 10 watts. And then that is assuming the following of a couple things, and I'm gonna post that. You're gonna be able to see that when I upload my PowerPoint. And then after that, we can determine that how important it is that he was moving forward. So, if Crosby was standing still and shot the puck with 10 newtons of force, there would have been no initial velocity. Therefore, the puck's final velocity would only be 9 meters per second. So it's quite a big difference when you're shooting and when you're just standing still. The next thing is we're going to be talking about turning potential energy into kinetic energy. This is turning potential energy into kinetic energy while shooting. So we're just doing another little energy graph rundown. So the first part of it is the chemical energy from the food you've consumed. And then as the player raises his stick up, he creates gravitational potential energy. And then he swings his stick down, and that's creating kinetic energy. And then as he makes contact with the ice, he loses some of the energy to thermal energy through friction, through thermal energy through friction of the blade and the ice. And then as he swings down and the puck makes contact, or the stick makes contact with the ice, when you're taking a slap shot, you're aiming to hit the puck just a little, or you're aiming to hit the ice just a little bit behind the puck, so your stick kind of snaps into it. So he hits the ice a little bit behind the puck, creating a little bit of elastic energy, and then the stick releases that puck, and shooting the puck forward, and that is creating some kinetic energy. And then there's some energy that's lost there through sound, and there's some energy lost to the sound energy when it hits the puck and when it hits the ice. So, and then the last thing I'm going to be talking about today is some of the physics behind the hitting in hockey, and how you can use the boards to protect yourself. So you can't see it right now, but I have two pictures that protect. There's two pictures. There's one. There's a player a little bit farther away from the boards getting hit, and he kind of goes head first in the boards. And then there's a player who's right up against the boards, and he gets hit, and he just takes. He just seems much safer. So this is because when a force is applied to an object, in this case the player, it'll accelerate unless slowed down by something in its direct path. So, for example, it could be the boards, and this is just an example of Newton's first law. An object will stay in motion, and an object in motion will stay in motion unless affected by an unbalanced force. For example, the boards, of course. And then I have a free body diagram of this situation, and you can see one can conclude that bigger players, ones with greater mass, will actually be safer when taking a hit. And then their greater mass will mean an opposing player will have to strike them with a greater force in order to move them at the same speeds. And then in order to eliminate any acceleration and velocity caused by a body check, players can brace themselves on the surface of the boards. This will allow for much of the force then impact to be absorbed by the boards. If there was 20 newtons applied on a player braced for a hit, the player will exert 20 newtons of force onto the boards, causing the boards to exert 20 newtons of force back towards the player. This is because Newton's third law states that for every action there is an equal and opposite reaction. In this case, the player will significantly reduce the risk for injury since their body is not going to accelerate and collide into anything. Thank you very much.